Welcome to This Explainer. Okay, today we're embarking on a massive, literally planetary-scale detective investigation. Long before humans ever started burning fossil fuels, Earth's climate was already constantly changing, right? I mean, swinging wildly between these scorching hothouses and deeply frozen ice ages. So we're going to examine the evidence, we'll look at the data, and try to uncover the natural suspects behind this incredible cosmic clockwork that drives global warming and cooling. It is an absolutely fascinating story of deep time and just incredibly powerful natural forces.
Okay, let's dive into this visual roadmap. We'll start with a quick intro to natural climate, then we'll systematically investigate each of our prime suspects: solar activity, volcanic eruptions, and the Milankovitch cycles. Finally, we'll look at climate amplifiers and the sheer anatomy of an ice age.
Section 1. Intro to Natural Climate. So to understand where we are today, we really have to look at the era we're currently living in, the Quaternary period. It covers roughly the last 2.5 million years, and it's basically defined by the continuous waxing and waning of these great ice ages. Which brings us to the massive question: is climate change a natural process? Well, the answer is a resounding yes. Before human impact was even a thing, Earth's climate was already an incredibly dynamic system, constantly shifted and pushed by very specific astronomical and geological mechanisms. I mean, our planet has seen over 50 ice ages in the last 2.5 million years alone. So who or what are the actual culprits behind these massive shifts? Section 2. Solar activity and sunspots.
First up, we turn our attention to the sky, to our most obvious suspect, the sun. It makes perfect sense, right? Fluctuations in solar radiation directly impact the heat we get here on Earth. And to understand this, we need to look at sunspots. By definition, these are small dark patches on the sun's surface, the photosphere, that are linked to intense magnetic fields and solar activity. But hey, don't let the word dark fool you. While they might look like little dark patches compared to the rest of the searing hot surface around them, they're actually blindingly bright to human eyes. They're basically the clearest visual indicator we have of exactly how active the sun's energy output is at any given moment.
Now, what's really interesting about this is how those magnetic field lines just burst outward and loop right between the sunspot pairs. The fundamental theory here is that fewer sunspots actually mean a lower overall heat output from the sun, and that of course translates to less heat reaching us on Earth, creating cooler temperatures for us down here. But, time scale really matters here. The sun has this regular, relatively short 11-year cycle of rising and falling sunspot numbers. But 11 years is way too short to cause a major, long-term climate shift. However, if we look back at historical records, astronomers noted this crazy 70-year period from 1645 to 1715, known as the Maunder Minimum, where there were almost no sunspots at all. Literally. And this drastic, prolonged drop in solar activity historically coincided with a freezing period in Europe and North America that we now call the Little Ice Age.
Section 3. Volcanic eruptions and cooling.
Okay, let's move from the heat of space to Earth's own internal heat. Massive volcanic explosions are our second major suspect, and they basically act like a giant atmospheric cooling filter. And this brilliantly illustrates how volcanoes do that. They inject huge amounts of sulfur dioxide straight up into the stratosphere. Normal eruptions, their ash just washes out of the lower atmosphere pretty fast. But major eruptions blast that sulfur dioxide up so high that it oxidizes and forms this immense haze of sulfuric acid droplets. This haze acts exactly like a planetary mirror, literally reflecting the sun's radiation right back into space and cooling the entire globe.
To put into perspective just how potent this cooling effect really is, consider Krakatoa. When it blew in 1883, producing a blast you could hear 3,000 miles away, by the way, it dropped global temperatures by a massive 1.2 degrees Celsius for an entire year, causing completely chaotic weather globally until 1888. Then there's Mount Pinatubo in 1991, which blocked 10% of normal sunlight, causing a 0.4 degree drop. But honestly, these are tiny compared to prehistoric supervolcanoes like Yellowstone. Models actually suggest a supervolcano could cause a devastating 6-degree global drop, and up to a staggering 15-degree drop in the tropics, and that freeze would last for years.
Section 4. The Milankovitch cycles.
Moving on to our third suspect, we're looking at the heavy science driver of the Great Ice Ages, Earth's orbital wobbles around the sun. These are named after the brilliant Serbian mathematician Milankovitch, who identified 3 distinct orbital parameters that literally change how Earth receives sunlight over tens of thousands of years. First, you've got eccentricity, which is the shape of our orbit slowly stretching from circular to elliptical over about 96,000 to 400,000 years. Second is obliquity, the changing tilt of Earth's axis on a 41,000-year cycle. And finally, precession, which runs on a 27,000-year cycle. Precession is exactly like the gyrations of a toy spinning top as it slows down, changing which hemisphere points the sun during our closest approach.
Let's see how this builds together. When you mathematically combine this eccentricity, tilt, and wobble, they drastically alter the summer insolation, meaning the amount of solar energy we receive specifically at 65 degrees north latitude. This specific latitude is absolutely critical. It's just south of the Arctic Circle. If the summer sun there is weak enough, the winter snow actually survives the summer melt. So year after year, it builds up, ultimately creating a massive continental glacier.
Section 5. Climate amplifiers and feedback. Now here is a fascinating twist. The Milankovitch cycles alone, they only produce a tiny drop in radiation. It's far too small to actually freeze the planet on its own. It requires the Earth's systems to hit the panic button to amplify those tiny solar changes. And the primary panic button is the ice albedo feedback loop. Let's walk through it. Step 1. It starts with a slight reduction in summer temperatures from those orbital wobbles we just talked about. Step 2. Because it's cooler, a little snow and ice manage to survive the summer. This triggers Step 3, increased albedo. White ice reflects sunlight back into space way better than dark land or ocean. And because more sunlight is reflected, Step 4 kicks in, the Earth cools even further, meaning the very next year, even more ice accumulates. A tiny orbital trigger literally snowballs into a massive, self-sustaining freeze.
And as those ice sheets expand, particularly the massive Laurentide ice sheet over North America, they trigger secondary feedbacks. They grew so mountainous that they physically deflected atmospheric wind paths, effectively blocking ocean currents like the warm Gulf Stream from moving north. By cutting off that supply of warm ocean water, the entire northern hemisphere was just plunged into an even deeper, inescapable cold.
Now, it takes up to 80,000 years for these feedbacks to slowly build a maximum ice sheet, but getting rid of it, that is terrifyingly fast. When the orbital cycles shift to warm the Earth, sea levels rise. This warm water completely undercuts the massive coastal ice sheets. It is literally like putting hot water under a tub of ice cream. This undercutting leads to total structural collapse, melting an 80,000-year-old glacier in a mere 4,000 years.
Section 6. Anatomy of an Ice Age.
So the crucial point is grounding all this abstract cosmic clockwork into the terrifying, awe-inspiring physical reality of the last ice age, about 21,000 years ago. 3,300 meters. That was the incredible thickness of the Laurentide ice sheet over Canada's Hudson Bay. We're talking over 2 miles of solid ice just crushing the continent. It extended all the way down to New York and Cincinnati. Over in Europe, the British ice sheet was so unimaginably massive that it acted like a giant bulldozer. It entirely blocked and rerouted the path of the River Thames in London to its current location.
And because so much of Earth's liquid water was sucked out of the oceans and locked up in these gargantuan ice sheets, global sea levels dropped by an astonishing 120 meters. To put that completely alien landscape into perspective for you, 120 meters is roughly the exact height of the London Eye. Just imagine that much water missing from the world's oceans. Now, we know greenhouse gases like carbon dioxide dropped significantly during these ice ages, which obviously helped build more ice. But I want to leave you with this absolutely fascinating, unresolved debate currently raging among paleoclimatologists. Do orbital shifts cause the cooling that builds the ice, which then alters ocean biology to reduce greenhouse gases? Or do the orbital shifts somehow reduce the greenhouse gases first, which then triggers the deep freeze? The jury is still completely out on this one. It just leaves us to ponder how incredibly intricate and beautifully fragile the balance of our natural planetary climate system truly is. Thank you so much for joining me on this deep dive.